function along a line. Let s equal f of t be the position along the x-axis as a function of time. The displacement of the object over time from t to t plus the change in t. So it could be like from 2 to 3, right? So from 2 to 3, where t equals 2 and the change in t equals 1, therefore making t plus the change at t equal to 3, right? So basically it's just a slope of a secant line. Slope of a secant line there. That's the average velocity. The instantaneous velocity is the derivative of the position function with respect to time at time t, right? So as this change in t goes to 0, well, then we get the slope of a tangent line, right? So that would be the instantaneous velocity. So how do we know, when we look at velocity, how do we know which direction it's moving? Well, it depends. If it's moving along the x-axis and the velocity is greater than 0, that means it's moving to the right, okay? And if the velocity is less than 0, then it's moving to the left, okay? What if the velocity is 0? Well, that means it's come to rest and it's changing direction. Okay, so less than 0 is left, greater than 0 is right, and equal to 0 is stopped. Okay, so the speed is the absolute value of the velocity. So let's say that velocity at time 2 equals -4, and the velocity at time 5 equals 4. Okay, so all that tells me is that both of them have the same speed, right? They both have the same speed of 4, but at time 2 it's moving to the left, and at time 5 it's moving to the right. Okay, so the definition of acceleration is the derivative of the velocity with respect to time. If a body's velocity at time t is v of t, then the derivative at that point is the acceleration. So how do we know if an object is speeding up or slowing down? Well, here's how we know that. If v of t and a of t have the same sign, right, are either both positive or both negative, that means they're speeding up, right? An object is slowing down if v of t and a of t have opposite signs. Okay, so just to sum things up here, I've got position, I've got velocity, and I've got acceleration. Okay, so the acceleration is the second derivative of position. The velocity is the first derivative of position. Let's look at an example. An object is traveling along a line with position defined to be that. All right, so this is our position function. Let t equal 0 be the starting point. Find the velocity and acceleration for this vector. So the velocity for this particle, would be the derivative, which is 2t minus 2. The acceleration would equal 2. So notice that the acceleration will always be positive. When will the velocity be 0? So let's set the velocity function equal to 0. So 0 equals 2t minus 2. That means that 2 equals 2t. That means t equals 1. What happens at t equals 1? Well, the particle is at rest. Particle at rest, right? Changing directions. When is the object moving left or right? I'm going to go off camera and put some stuff up and explain. Okay, so I sketched my velocity function 2t minus 2. This blue point here is the point where it's going to change direction. So before that point, based on this graph, our velocity would be negative, which means it's moving to the left from 0 up to 1, but not at 1. And then it changes direction, so it's moving left, Right, it's moving left along this line, and then at time 1 it stops and it starts moving right. So let's draw ourselves a line graph of the motion of this particle. Alright, so here on this next slide, I've created a line graph of this motion particle, okay, and this right here, this green point, is where the position was at the start, where t equals 0. So I used my position function, I plugged in 0, I got 1. I knew based on the last slide that I was going to be moving to the left until I hit t equals 1. Right? So the position at t equals 1 is 0, and then it started to move back to the right. So here's t equals 2, and over here is t equals 3. I used each of these right here to show me those positions so that I knew where my particle was at what time. So is the particle ever speeding up, and how would I know? I'm going to go off camera and do a little bit more with part E and F. Okay, so for part E, is the particle ever speeding up? We said the particle would be speeding up if the signs of the velocity and the acceleration were ever the same. And it looks like they will match up as being the same when t is greater than 1, right? Since a of t is always positive and the velocity is always positive after 1, we can say it's speeding up. It's speeding up from 1 to infinity, right? Now, is it slowing down? Yes, it is. It slows down where the signs are the opposite. So a of t is always positive and v of t is negative between 0 and 1. So it's slowing down from 0 to 1. Okay, so in part G it says, what is the maximum speed on the interval from 0 to 4? Okay, so if I were to sketch this, right, our velocity function looked kind of like this, right? Our velocity was 0 at time t equals 1. And then we want to go out to 4 and back to 0. Right? So t equals 4 and t equals 0. Well, I'm just going to test these endpoints. I'm going to test the endpoint here at time t equals 4 and the endpoint here at times t equals 0. And then find the speed. So the speed would be the absolute value of the velocity at time t equals 0. So I'm going to plug a 0 in there. So 2 times 0 minus 2. Well, that'd be negative 2, absolute value of negative 2. Looks like the speed at that time is 2. I don't know units of measure, but that's what it is. Let's test the other point. That'd be 2 times 4 minus 2, which would be equal 8 minus 2, which is 6. Absolute value of that is 6. So the maximum speed would be at time t equals 4, and that speed would be 6. Okay, in part H it says, what is the total distance traveled during this time from 0 to 4? Now this is different than displacement. Okay, displacement and total distance are different. So what I want to do is I want to test or find the distance traveled on 2 different intervals. Okay, I want to find the distance traveled to the left and then the distance traveled to the right. And I want to add those 2 together. Right? So first let's think about the distance traveled to the left. Okay, so I'm going to go on this interval from 0 to 1, find this distance, and then I'm going to go from 1 to 4 and find that distance. So what was s of 0? I think we said s of 0 was 1, and position for 1 was 0. So the total distance traveled, even though it was to the left, is 1 unit. Okay, the distance traveled in this second interval, again, we know that s of 1 is 0, and s of 4, oh boy, what was s again? S was t squared minus 2t plus 1. So 16 minus 8 plus 1 is 9. So s of 4 is 9, therefore the distance traveled there is 9, and the total distance traveled overall to the left 1 unit and to the right 9 units, so it looks like 10 units. Okay, all the way back to 1999, this is a free response question on the calculator portion of this test. A particle moves along the y-axis with velocity given of that, where t is greater than or equal to 0. In which direction, up or down, is the particle moving at t equals 1.5? Okay, you're going to need your calculator, so let's figure that out. I'll be right back with an answer. Okay, so all I did was I typed this in, my velocity in is y1. And for part A, I literally just did y1 of 1.5. It took me about 10 seconds. I got 1.167, which tells me that this particle is moving up. Okay, don't make the mistake of writing to the right, because you would definitely be wrong. They would mark you for that. So why is that? Because v of t is greater than 0, therefore it's moving up. Okay, in part B it says find the acceleration of the particle at time t equals 1.5. So I'm going to use math 8 for that. Is the velocity of the particle increasing at 1.5? Why or why not? Okay, so I'm going to find the velocity at 1.5. If that is also positive, the speed will be, the velocity will be increasing. If it's not, then it won't. So I'm going to go off camera here, use my calculator for a moment, be right back. Okay, so I get y1 prime at 1.5, which is equal to the acceleration at 1.5 to be negative 2.048. Therefore, since velocity of 1.5 and acceleration of 1.5 are opposite signs, the particle is not speeding up. Not speeding up. Okay, let's get through one more example and that'll be good for today. Okay, so it's just something to be aware of, right? I plugged this in for my function. Here is my position at time t equals 0. So I'm going to say x of 0 equals 1. Find the acceleration of the particle at time t equals 2. Is the speed of the particle increasing at t equals 2? Why or why not? So let's find v of 2. And then let's find a of 2 using math 8. Compare them, we'll see if the speed is increasing. Velocity at time t equals 2 is negative 2.727. So I see here that the velocity and the acceleration, okay, are different signs, therefore the speed is decreasing. Okay, so for part B, find all times t on the open interval from 0 to 3 when the particle changes direction. Okay, so I want to know when the velocity is equal to 0 between t equals 0 and t equals 3. I'm going to need my calculator. I'm going to go ahead and graph that, and I'll put a little sketch up in a moment. Okay, so something interesting here. The particle, there's a difference between the particle at rest and the particle changing direction. So here is something you're going to need to know. First of all, I found out where the velocity between 0 and 3 equals 0. However, the only reason that the particle changes direction here is because the derivative goes from negative to then positive. If you had a point on this graph, let's say it looked like this. Okay, let's say the velocity equaled 0 there. It didn't change direction, it just came to rest and then continued in the same direction. So you have to then check. So what I would say is that the velocity is less than 0 to the left of 2.506, okay, or on this interval from 0 to 2.506, and then the velocity changed to then being positive when we got past 2.506 up to 3, we could say. We don't really know or care.